Good afternoon, everyone. We are going to get started in about 1 minute, one more minute, and we will kick off just letting folks dial in. All right, folks, let's get started. It is 1:01 on this Thursday, November 7th. Thank you for joining us for the 48th webinar in the Offshore Wind Series, Learning from the Experts. I am Jess Deely, Senior Advisor with NYSERDA's Offshore Wind Team, and it is my pleasure to be joined by today's expert, Dr. Bruce Bailey. Before I introduce Dr. Bailey, a few reminders for participants and some background on this webinar series. Firstly, if you are experiencing any technical issues, please contact Adam Hawk at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars from the Learning from the Expert series are available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions to all panelists. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable energy sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov or fill out a survey also available on our website. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. It is now my pleasure to introduce Dr. Bruce Bailey. Dr. Bailey has worked for over 4 decades in the renewable energy field. His career began as a research associate at the University of Albany's Atmospheric Sciences Research Center, where he became the manager of wind energy programs. He eventually left the university to run the technical consulting firm he founded, AWS True Power, which specialized in meteorological and engineering-related services for the clean energy and air quality sectors. The firm was acquired by UL, a global safety science company, where Bruce became the VP for renewables. He retired from UL at the end of 2019 and is currently the executive in residence at the Center of Excellence in Weather and Climate Analytics at the University of Albany. Bruce also serves on multiple boards, guest lectures, and supports MetOcean research. He has an undergraduate degree in atmospheric science and a doctorate in engineering management. Thank you, and I will now hand things over to our speaker, Dr. Bailey. Take it away.
Hey, thanks, Jess. And hi, everyone. Uh, there's two questions I aim to address today. One is how are offshore wind turbines, including their support structures, designed to withstand the relentless elements and the occasional extremes over their lifetimes? And those lifetimes are at least 20 years, but more like 25 to 30 years, if not more. And then the second question I want to address are, what are the event types that drive these weather extremes? Giving focus to the New York Bight region as well as the northeastern U.S. Next slide, please. So different items that I'll be talking about today. First, I'll be starting off with a global perspective. Where has offshore wind energy come from? What have we learned about it? Then I want to categorize the primary event types that cause extreme wind and wave conditions. I want to describe the mid-ocean environment. Now, mid-ocean is a newish term. It's really a combination of meteorological and oceanographic. So we just call it mid-ocean for the offshore wind industry. Then I'll be talking about just how wind projects are designed for normal and extreme conditions and describe how extreme probabilities are estimated, particularly based on relatively short-term on-site measurements. And I'll talk a little bit more about risks from East Coast storms, how often they occur, how extreme they get, and also how those risks may change with climate change over the upcoming decades. Next slide. So offshore wind has been around for over 30 years. The first offshore wind farm was installed off the coast of Denmark back in 1991. And since then, over 300 offshore projects have been built and are operating today. And as you can see, they total actually over 75 gigawatts of capacity, which is still it's less than 10% of the overall global wind capacity, which is dominated by land-based installations. But offshore wind is growing at a faster pace than land is today. As you can see, concentrations of offshore wind can be found in two main areas, one off the north coast of Europe, and then also off the east coast of Asia, especially off China and Southeast Asia. China, in fact, is dominating the offshore market now and has the majority of the capacity to date. But over here in the East Coast of the United States, you can see a few dots there. All the green dots mean these are projects operating, and yellow are those under development. And so that's becoming a significant market. It's about 40 gigawatts anticipated over the next decade or so in the U.S., with lots more thereafter. And one of the things that the U.S. market for offshore wind has in common with its European and Asian counterparts is the exposure to harsh, weather conditions and extreme events. Extreme events in Asia, East Asia, are primarily dominated by typhoons, which is their term for hurricanes. And actually, that's the most hurricane-prone part of the country, of the world, I should say. In Europe, particularly in the North Sea, very strong winds. The waves are not quite as strong as they are in the Atlantic, but all sites experience just harsh conditions, and I'll be getting more into that in a moment. Next slide, please. Now, the northeastern U.S. enjoys a lot of passages of weather systems, typically every few days, and that helps create a windy offshore environment with annual average wind speeds on the order of 10 meters per second or more at height. So that's why it's an attractive location for offshore wind. But the main types of extreme conditions come from three primary sources. And I'll be focusing more on them later in the talk. One are tropical cyclones, which another term for hurricanes when they get particularly intense. These are storm systems that originate down in the tropics, usually below 30 degrees latitude. Now, for context, 30 degrees latitude is equivalent to the northern border of Florida. So hurricanes and tropical cyclones, they typically develop in warm water. And the warmer the water, the better for strong storm development and larger storms. Another type of key event are extratropical cyclones, a fancy term for really low pressure systems or storm centers that develop in the middle latitudes, so outside of the tropics or extratropical. And when they develop into coastal storms along the east coast of the US, which are famous for heavy snowfalls, they're also well known for very strong winds and high waves, and they are typically called nor'easters. And these occur much more frequently than hurricanes in this part of the country. And then last are squall lines associated with typically cold fronts, but they're clusters of heavy thunderstorms, which can really create sudden gusts of wind and strong waves. But they're not typically not as responsible for extreme conditions in the Northeast as the other two types of events. So I'm going to be focusing on those two events here on. Next slide, please. So this is an illustration of the various external environmental factors that wind systems need to consider. They consist of a whole gamut of meteorological and oceanographic parameters. Above the waterline, of course, the most important atmospheric factor is the wind, which varies both in speed and direction, and also varies with height, which is otherwise called wind shear. Of course, other important factors that you can see there are temperature, pressure, humidity, air density, precipitation, and even lightning. And then below the waterline, and including the surface, the waves are the most important parameter, and they're characterized by their height, their frequency, their direction. And other parameters are storm surges, water levels, and currents. Another important parameter, it's really not a met-ocean one, but it's the seabed and its composition. One of the design objectives of a wind turbine structure is to transfer the loads imposed by the winds and the waves on the structure into the seabed. So the seabed is an important component of site characterization. Next slide. So the whole family of met-ocean parameters can really be grouped into three categories, as you can see here: atmospheric, ocean, and then at the bottom, joint distributions of both, because extreme conditions that offshore wind turbines must endure usually come from storms that have a combination of strong winds and rough seas. As I mentioned already, wind turbine design is mostly driven by winds, and foundation design more by waves. And measurement campaigns are an inherent part of offshore wind project development. And it's the reason why dedicated campaigns are deployed on the order of 2 to 3 years for project areas. Next slide, please. So I want to get into sort of design standards that offshore wind turbines and even land-based turbines follow. And there's a widespread practice for the wind industry to follow IEC standards. IEC stands for International Electrotechnical Commission. And these standards come about through an industry collaboration and peer review process. They're updated periodically. And you can see a couple of standards listed there. One applying for fixed offshore wind turbines, and the other one for floating offshore turbines with floating, of course, coming more and more into commercial viability. They tend to be deployed more in deeper water, say deeper than 60 meters in depth. So a key element of the standard, which really applies to the rotor and the cell assembly of turbines, everything that goes on top of the tower, is shown here, where turbines generally are defined or categorized by wind regime. And there's different classes of turbines that are manufactured. 1, 2, and 3, as well as S and T. As you can see that there are different wind speed thresholds that tend to dominate the definition of each of these categories. So for a category 1 wind turbine, it's really designed for a site that has an annual average wind speed at hub height on the order of 10 meters per second. And then you can see for lighter wind regimes, you have the other classes. But there are other qualifiers, such as the extreme 10-minute speed, which would occur perhaps once every 50 years. So that's 50 meters per second, or 112 miles per hour, if you're more comfortable with that unit. And then there are considerations for tropical storms, and that's a 57 meter per second speed. And then even for short gusts, a 3-second gust, again, occurring maybe once every 50 years, 70 meters per second. The T class of turbines that are designed are made more for tropical cyclone or typhoon prone regions. And S-type turbines are designed for systems that maybe fall outside of these other categories. So to boil it down, for, say, the northeastern U.S., Class 1 turbines are primarily used and will be used going forward. They're quite compatible with the wind regime that exists in this part of the country. Next slide, please. So there's more to the IEC standards and the definitions of classes than just those sort of wind categories. But there's also a lot of additional analysis that needs to be done for really a whole variety of what are called design load cases. And this represents the different operating states of the turbine being exposed to different wind and wave conditions concurrently. So there's, for the different operational modes of the turbine, you're testing it during its startup mode, when it's fully operating, when it's shutting down, when it's parked. And so you're running a series of load cases that deal with fatigue. And fatigue is really defined by that stressing on a repeated basis, the cycling of waves, the cycling of winds, just those ongoing impulses, if you will, and the response of the materials of the turbine to that. These materials are designed to withstand cycling on the order of millions of cycles, if not hundreds of millions of cycles, depending on the parameter, the winds, the waves, and so on. Then there are ultimate load cases where you're looking at sort of worst case conditions for a combination of wind and waves, as well as some fault modes for the turbine. If it's not operating correctly, things could go sideways as well. So you're testing for all eventualities, if you will. And so there are software packages designed to operate and to run these models, these load cases, which do rely on having accurate med-ocean information to feed these models for the site in question. And they're quite complex. You know, they couple modules with aerodynamics, you know, from the wind turbine structure, hydrodynamics from below the waterline, the structural dynamics, as well as just the dynamics of the electrical and control systems that are integrated into the system. Next slide, please. Now, like all standards, they don't cover every potential eventuality in every spot in the world, but they cover the large majority of them. And they do provide a standard that the industry can follow and certify projects for. As I mentioned before, those particular standards I mentioned apply just to the rotor and nacelle assembly mounted on the top of the tower. The rest of the structure needs to be designed for site-specific conditions following other standards. And those site-specific conditions include water depth as well as seabed composition. Some things that the standard doesn't account for is things like wind veer, which is the change of wind direction with height across the rotor span. Also, some of the assumptions made for conditions like wind shear, the change of wind speed with height, may be more severe for certain tropical storm situations than the assumption defines. So that's just contingent on the designer of the project to make sure that the ultimate design is able to be responsive to the conditions predicted for the site in question. Next slide. Some other things that need to be kept in mind are items such as scouring of the seabed around the foundation of the foundation, dealing with the safety of cabling. In most cases, it's jet plowed into the seabed by a meter or more, but some surface conditions near the seabed surface, strong currents sometimes during storms can erode that sand, if it is sand, and expose cables. So all those are considerations. And substations also have their own set of standards. They also tend to have longer return year periods, not the 50-year return period that you saw with the wind turbine standards, but they'll have a 100-year period or longer for some extreme events as well. So these are all considered part and parcel of designing offshore projects. And certainly standards as well as industry experience, they draw from, say, the offshore oil and gas industry, for example. So there's a lot to have been learned from those industries as well as from the 30 plus years of offshore wind projects as well. Next slide, please. So I mentioned that there are other standards that are applicable for designing projects. I've already mentioned the IEC, but you can see there's lots of acronyms here: ISO, the API, DNVGL, and American Bureau of Shipping, because there's a lot of shipping-related activity involved with transporting and installing these projects as well as servicing them. Also, the Bureau of Ocean Energy Management, part of the Department of Interior, that sort of oversees the leasing of offshore wind areas for the U.S. They have a lot of guidance as well, where they'll consolidate a lot of this information and make it available to the industry. Next slide. So let's talk a little bit about how long-term mid-ocean conditions are determined for a site. Particularly when you're just measuring conditions for 2 or 3 years. And this is similar to what one does on land for wind projects, for solar projects. And basically it's using that measure, correlate, predict method, MCP, where you're taking the short-term measurements, but you're correlating them with another site in the vicinity that has been collecting data for a long period of time. And based on the correlation for the short-term site's monitoring period, based on that correlation, you've got a mathematical relationship between that site and that long-term stations, that site. And then based on that relationship, you can reconstruct sort of historically, it's a hindcasting methodology, where you're just reconstructing what the historical record for your site is through those correlations with that long-term site. A very popular database that's used as a correlation and comparison point is called reanalysis data. And it consists of a consolidation of all sorts of surface and upper air data that's been developed in a gridded format that covers the entire globe. And it provides consistent spatial and temporal database that is pretty accurate. I mean, the ERA 5 reanalysis data set is the best there is today, and there'll be newer versions coming in the future. A National Data Buoy Center, they're weather buoys. They've been around for, say, 40 years or more. Not all of them, but many have been. So they're another long-term reference point as well. So I've already mentioned that that's how one can reconstruct a long-term data set for a site in question. And then that brings us to, well, how do you then use that data set to determine extreme values or return periods, like, well, what's the worst that's going to happen in the next 50 years kind of calculation. So the next slide, please. So there's a general technique called extreme value analysis. And this deals with the statistical analysis of extreme events, which occur very rarely. You know, they may only occur once a year in the case of hurricanes, and maybe 5 times a year in the case of nor'easters. So you're dealing with a relatively small data set, and you're looking to fit a distribution, a long-term distribution. And one of the things to keep in mind is that when you have what I'll call a mixed climate, where you have hurricane type events, which are creating extremes, then you have nor'easters creating extremes. It's better to treat them as separate populations and to do the extreme value analysis separately to see what kinds of results you get. You can also do that with squall lines as well. And as one moves further south down the East Coast, you'll see squall lines playing a bigger role because the nor'easters aren't as active further south of, let's say, the mid-Atlantic states. And there's various modeling techniques and statistical treatments that can be used, and then one can come up with return year periods for just 50 years, but 100 years, 500 years, and you can just keep going. Next slide, please. So let's look at what some of the extremes are off the East Coast of the U.S. And I'm drawing this information from a couple of studies. One, the upper table came out of a team at Cornell University. And this is for projects that are circled there. And it's the pink or salmon covered lease areas. And so in the upper table, they calculated, oops, just go back a slide, please. Backwards, please. There we go. Good. Thank you. So they determined, let's say, for Massachusetts, Rhode Island, so the area is just south of Massachusetts, that VREF, or that 50-year maximum 10-minute wind speed at 100 meters above the surface, with speeds on the order of 39 to 44 meters per second. That's what you could expect. 40 meters per second is equivalent to 90 miles per hour. Looking at significant wave heights, again, a 50-year return period, you're looking on the order of, say, 9 to 11 meters per second and for that particular locale. And a significant wave height, of course, what is that? And that's really the average of the top third highest waves. So that's a commonly used statistic to define the wave environment. And then the max height value are shown there in the right column. And so the variations depend on which project you're talking about, and lower values tend to correspond with sites that are closer to shore. And then the bottom table is from another set of researchers, including the University of Massachusetts at Amherst and some other universities. But they looked at 150-meter hub height. So you'll see higher maximum wind speeds shown there and equivalent significant wave heights. So that gives you a flavor of the quantity of extreme winds and waves. Let's go next slide, please. So one of the things that I did this past summer was use this ERA 5 data, and it goes back to 1940. So looked at, well, what were the highest winds experienced at a midpoint of these offshore lease areas, and I have it circled there on the map. And for those maximum speeds, what event did they correspond to? And you can see the speeds, max hourly speeds, got up to almost 44 meters per second at that one particular locale. But you can see the event type in the right column there is that the large majority of high events were hurricanes. And so that is one of the features of this region, is that by and large, the max winds come from hurricanes. Hurricanes are relatively rare in this region. But you will see a couple of other items there, like item 6 and number 8, where there are storms that are more associated with nor'easters. Another thing I wanted to point out here was that in the date column, there are 5 dates where we're seeing extreme winds occurring anytime between the period of 1950 to 1961. And I'll talk a little bit more later about, well, why was the decade of the 50s, so active with hurricanes. Another thing I wanted to point out before we go to the next slide was that item 7 here, Hurricane Carol, was a Category 3 hurricane, and it's the only Category 3 hurricane on this list. And there hasn't been another Category 3 hurricane impacting this region since 1954. The previous one to that was in 1938. And then the one before that was in the 1860s. So Category 3 hurricanes are quite rare. Next slide, please. One thing I want to point out too is just the nature of hurricane winds and how they correspond with the category definition for hurricane. So it's important to realize that a category for hurricane is defined based on the maximum sustained winds observed in the hurricane. And it's also at 10 meters height. But the high sustained winds tend to be at the eye wall. And so in the bigger picture here, you can see the big swirl of clouds. And that's quote unquote a hurricane. But the red circle really defines the smaller portion of that swirl that really is experiencing hurricane force winds. And it's only the eye, or the region very close to the eye, that is experiencing the category definition. So if it's a Category 3 hurricane, it's really in a very small portion of that storm. But much of the swirl there you can see is less than hurricane force winds, but it still falls in the field of the quote unquote hurricane. So this just has meaning when one looks at the exposure of wind farms in a hurricane prone region, that the max winds are really experiencing only a very small portion of the path of the hurricane itself. Next slide, please. So if it's a hurricane, if it's a squall line, if it's a nor'easter, how do wind turbines ride through the storm? And so what is typically done, large scale turbines, they'll typically cut out at 25 to 30 meters per second, depending on the turbine model and the features that it has. The blades are fully feathered. They're feathered to go to near zero. Then the yaw drive, which constantly points the rotor into the wind, that remains active because it's important to face the rotor into the wind even as the wind direction changes. And so in these extreme storms, particularly hurricanes, directions can change quickly. So it's important to manage loads to keep that yaw drive powered up and active. If the grid goes down during a storm like this, how do you keep that yaw drive active? And typically offshore turbines will have an emergency power supply. It could be battery based or otherwise, but it will have onboard energy in order to keep systems going and keeping that yaw drive active to keep it operating in a safe mode. And then when winds eventually subsides, and they fall below 25 meters per second, the turbines can start operating again. Next slide, please. So this is another top 10 list, but this isn't for extreme winds. This is for longest duration storms. This is for when winds are blowing, say, above 22.5 meters per second or more. And it's for the same site as before. And if we, again, look at the event type, it's dominated by nor'easters. So these winter coastal storms. There is an occasional hurricane sprinkled in there, including Hurricane Sandy, which interestingly, made the top 3 for this particular site. So these longer duration storms, they're just creating a lot of these loads, these cyclic loads, and just sort of pounding the turbines. So they're helping in some way accelerate the fatigue loading. But this is just something to consider in the original design work for the project. Let's see if there's something else I wanted to point out here. One thing I did want to mention was that I keep pointing out this particular project area because it's centralized, but the more extreme conditions that have been observed have been, in terms of extreme winds and extreme waves, are for the areas south of Massachusetts, say in the Vineyard Project area and the other projects that are planned to be developed. It's the most exposed there, so you tend to get the highest extremes there compared to the other projects to the south and southwest. Next slide, please. We could talk a little bit more about East Coast storms and the nor'easters. They're a significant phenomenon, not only because they can have strong winds that come close to hurricanes, and typically they can reach up to Category 1 hurricane strength, but they're also colder. The air is denser. So the ultimate loads that are placed on turbines and turbine structures can be just the same or close to it as hurricanes. And nor'easters occur much more frequently. There's an average of 12 storms per year, with 3 of them considered strong. Of course, the peak occurrence, it's in January, February, but occur anytime during the winter into early spring and even late fall. There's also been seen some interdecadal variability, and I'll show a graph of that in just a moment, where there are other influences, such as the El Nino cycles that we all have heard about. But during an active or positive El Nino period, there tend to be more nor'easters than in other periods. And when we get to talk a little bit more about climate change and modeling what that future might look like in terms of storm events, studies have shown that nor'easters may decrease in frequency, but the intensity or the number of strong nor'easters may actually increase. There's also been some suggestion that the track will move somewhat further east as well, but it's still early days when it comes to this type of modeling, so we'll just see how that turns out. Next slide. The graph on the left is a graph just showing the cyclicity, the variability in hurricane frequency in the Atlantic. Going back to the 1850s, some of these data obviously had to be sort of reconstructed or synthesized because we didn't have satellite imagery going way back. You have to look at ship records and other records to reconstruct the records going back that far. But due to some oscillations in Atlantic currents and other multi-decadal oscillations on a global basis or regional basis, there's a linkage to the frequency of hurricanes. Volcanic activity, dust to loading variations can also be a factor here as well. What I want to point out here is back in that table, that first table I showed you about the windiest years and the events that they corresponded to, particularly in the 1950s, you can see that peak in the 50s that occurred. And so there have been other peaks as well. This graph suggests we're sort of in a peak period, but that could be declining in the future, depending on what climate change brings us. On the right side are really the tracks of the storms that have impacted southern New England. There have been about 30 of those since 1851. Next one, please. Talking a little bit more about the 1950s, the upper chart here just shows the tracks of major hurricanes that struck or came close to the East Coast. And you can just see a lot of activity in that decade. But if you look in the 1960s, 1970s, nothing along the East Coast. 1980s, there was one event. But so it's not a constant in terms of expectations for hurricanes. They do vary over the decades, and that variability can be obscuring what may be happening due to climate change itself. So trying to sort the different types of variability is a challenge. Next, please. National Hurricane Center has developed return year periods for hurricanes all along the U.S. coast, and this is showing the estimated return period for all categories of hurricanes passing within 50 nautical miles of locations along the coasts. And as you can see, In the New York Bight region, anywhere every 13 to 20 years generally. And as you go further down the coast, of course, where they're closer to hurricane activity, it can be every 5 to 10 years. And similar numbers along the Gulf Coast. Next slide. This slide is dealing with major hurricanes, category 3 to 5. And you can see that in the New York Bight region, the return periods are more like 50 to 75 years. And as I mentioned, from the records that go back at least 170, 180 years, there have been about 3 category 3 hurricanes that have moved through this area. So next one, please. So just a little discussion about climate change considerations, because they do need to be brought into the design equation and planning for offshore projects, because they're designed to operate for the next 30 years or so. And so things may change. And with a very high degree of certainty and confidence, ocean temperatures will continue to warm and sea level will continue to rise. And so one of the considerations that brings to mind are the increasing risks are port facilities that are servicing offshore projects, as well as their associated land-based substations. And so in the design process, accounting for higher tides, storm surges, deluges of water, heavy precipitation and flooding. As we saw with Hurricane Sandy, those considerations should be brought to bear just to have greater resiliency for infrastructure, for more extreme events, and for new facilities like ports servicing offshore projects. That's something that they should be considering as they're under development. And as I mentioned, project designers are incorporating climate change risk. Of course, there's a lot of uncertainty in terms of, well, what does that look like? Will there be more storms? Will they be more intense? And so some ways in which this is being addressed, and even turbine manufacturers are helping to address this, where they're exceeding the IEC thresholds for speed for those categories that I mentioned. And but also designers can look at longer extreme return periods to help bring in more conservatism into the design of the project. They can build in larger safety margins or engineering because safety margins are part and parcel of designing systems as well. Next slide, please. And this is one of my final slides. And it's a messy slide, and I really want you to focus on the Atlantic box here in the upper right. And this is really a consolidation of climate change forecasts with a global warming of +2 degrees Celsius. And it's a summary of impacts for severe storms that the Geophysical Fluid Dynamics Lab has put together. They're a part of NOAA. And so looking at hurricanes in the Atlantic Basin, what does it look like with a warming planet? And a number of studies have suggested that the number of tropical storms and hurricanes will decrease, perhaps on the order of 15% on average. But the number of very strong hurricanes, category 4 and 5, would increase, let's say on the order of 10%. And that the strongest winds would increase marginally, let's say 3%. But rainfall rates would increase significantly, and storm inundation levels due to increased sea level rise by the year 2100, 2 to 3 feet sea level rise. So these are just suggestions, and these kinds of trends are pretty global as well. So it's just some of the feedback that climate change modeling is able to provide to give us a sense of how things may look like with the rest of this century. Next slide. This my final slide. So I just wanted to summarize that wind turbines are available as class types. They're designed around given wind regimes, whereas towers and foundations are more customized for site conditions. And the commercially available class 1 turbines, they're quite robust, and they're suitable for conditions here in the Northeast US. I mentioned too that nor'easters and hurricanes, they produce the most extreme mid-ocean conditions in the region, with nor'easters being the more common phenomenon and it's more cold weather phenomenon. Hurricanes happening other times of the year, but occurring much more rarely. And also changes in extreme weather. There's some suggestions of what that might look like, but they are factored into project planning. So next slide. I'd like to thank you for your attention, and I'd be happy to entertain any questions you may have at this moment.
All right. Thank you, Dr. Bailey, so much. We do have some questions coming in from the audience. Very good presentation. A lot of people were engaged here. So one of the main questions that we've seen so far is, you know, you talked about the fatigue with turbines. Is it your conclusion that the major fatigue factor for turbines is caused by major storms?
No, it's really more normal conditions. Fatigue loads really are the driver for the design of turbines and the support structure. It's not the ultimate loads. They're designed for the ultimate loads, but the main driver really is that long-term fatigue loading, which are, again, is the normal spectrum of the whole family of winds and waves and the joint distribution of both. That is the design driver.
Very good. You know, we're getting a lot of questions about just the impact of climate change and the use of kind of reanalysis data, looking back into the past, but we're seeing such a shift when you look forward into the future. So how are forecasters handling the impacts, that climate change is making on 50-year wind speeds when we see extreme weather more frequently than ever? So what once was a 50-year wind speed becomes more frequent.
Right, and that's, well, one example is some of the type 1 turbines that are commercially available for offshore wind, let's say 15 megawatt scale family of turbines. Instead of the 70 meter per second sort of extreme wind, they're rated for 80 meters per second. So they themselves have, say, some built-in margin, if you will. But also the other design elements, such as safety margins that I mentioned, you're always looking to have sufficient safety capacity, if you will, for conditions that will exceed those extremes. And typically these extremes are brief in nature, and the turbines are designed to take on those extremes.
Great. We're getting a lot of questions about temperature, right? So we know with climate change, our jet stream has just been put into the dryer, if you will. So we're seeing very intense cold periods and very intense warm periods. What's your take on icing, on what, these extreme cold periods that the Northeast face now more frequently than ever, where we get these major cold blasts? How do the turbines stack up against this, and what are the impacts to icing on this type of infrastructure?
Sure. There's a couple of types of potential icing on turbines. Of course, one is sea spray, but usually the sea spray doesn't reach up high enough to have a significant impact on the blades. So the other type of icing would be, say, some freezing rain or rime icing if there's some super cold cloud out there. But that's going to be a rare phenomenon because during these strong storms, even nor'easters, over the ocean, temperatures generally are above freezing, whereas inland it's below freezing or somewhere there's that rain snow line. And that's always the big trick in weather forecasting is who's going to get the heavy snow, who isn't. But offshore, you tend to be in the warm sector of the storm. So icing is going to occur very infrequently. When it does occur, they're designed to withstand icing just as land-based turbines are. But it's not deemed to be a significant probability or concern. I might mention that cold weather operations, they can be curtailed when temperatures do get below freezing or well below freezing for offshore. And there's even some curtailment when it gets pretty hot, say above 90 degrees, or even cooler than that, above 80, 85 degrees Fahrenheit. But it's not curtailment, just sort of scaling back on production.
Mm. And I know onshore turbines have some de-icing systems as well. I don't know that they're being deployed in offshore systems, but something to note as well for the audience. You know, this is a question that the public asks us often. You know, if a major storm comes through, will all the wind turbines included in a wind farm shut down at the same time, and won't that impact our utility grid in a negative manner?
Right, right. Well, first of all, let's say there's multiple offshore wind projects, and one could look at that scenario where like, gee, could they all just go down at the same time? And the answer is like, no. And the reason for that is that, first of all, you know, so strong winds start approaching a wind farm. There's certain turbines that are more exposed than others. Let's say the front edges of the wind farm. Those will see the strongest winds because other turbines, say back within the array of turbines, they're seeing lower winds mainly because of the waking effects from upwind turbines. So you'll be getting some staged shutdowns of turbines as the winds increase and the storm approaches the project. And so the more leading turbines and leading rows will be shutting down in a staged effect. Also should mention that offshore wind farms, the power curves for turbines also are not just cutting off at 25 meters per second, but more turbine models have a more gradual ramp down between 25 and 30 meters per second. So that provides some more gradation, you know, in shutdowns. And then lastly, these storm winds are very forecastable, and grid operators have lots of lead time to know when the risks of a shutdown of offshore projects will occur. And so they can be well prepared to have other generation available to replace whatever is lost whenever those offshore wind projects go into a shutdown mode.
Yeah, we're getting some questions, you know, looking nationally and internationally at how turbine infrastructure has held up to any named storms, or looking overseas globally, how have the foundations and towers held up? Do you have any specific examples of this type of infrastructure, offshore infrastructure, being hit by a major named storm, and how well it withstood that?
Yeah, there's various anecdotal information, but also just some published information too about, let's say, projects off the coast of China, some major typhoons, where projects have largely survived and ridden through. But in some cases, you'll have primarily blade damage occurring with a small fraction of the turbines. And so those are repairable, replaceable. In some cases, a damage like that may be insurable as well. So it's not as major an economic impact as it could be. So that there have been incidents of damage from very extreme storms, but they've been repairable and replaceable, and overall projects have not been sacrificed.
Very good. I think given the time, we'll ask one more question and then wrap up here. How does the public find more information on things like the operational practices or the power curves for wind turbines?
Boy, the best way is just to search online. There's a plethora of information out there that describe the fundamentals, but also describe advancements in the industry. Uh, Much of the standard operation of turbines, like the description of a power curve, for example, has stayed relatively constant over the years. Uh, and there's a lot of graphics out there and explanations. Uh, so I guess that would be the place where I point people to. Um, so wish them well with that. There's a lot of very good information out there. I know NYSERDA has a website that has lots of informative information. U.S. Department of Energy, NREL, the National Renewable Energy Lab, lots of information and publications are available to describe the technology and also where it's going.
Very good. Well, you answered that quickly enough. I can do one more. And I don't know that you're going to have an answer for this, given that your expertise is in atmospheric science, but curious if you've heard anything. We're getting questions on how often turbine blades need to be replaced. Do you have any insight into that?
I can wave my hands and thank you for the qualifier that I may not be able to answer this very well. But I mean, they're designed to last 20 years or longer. Uh, so, are they designed to last as long as every other element of the project? Of course, the blades endure a lot of flexing and a lot of fatigue and leading edge erosion and other types of impacts. They're exposed to the UV light. There are different ways in which they can deteriorate. So that's why there's a lot of inspection done, not only for the blades, but for the other components of the entire turbine structure. And if there are ways to treat blades or repair cracks, but in terms of a standard answer to how often they should be replaced, I can't give you a sound answer to that. I think it sort of varies, but the industry is moving more and more toward, longer duration blades.
Very good. I think we can leave it at there for now, given we're 2 minutes from the top of the hour. And just so participants know, we have gotten questions that asking for the slides. All of this is shared on our website and on our YouTube channel. So thank you for joining us for this Learning from the Experts webinar. A reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next webinar in the series will be on Wednesday, November 20th. Walt Musel with the National Renewable Energy Laboratory, NREL, that Dr. Bailey just mentioned, will discuss the benefits and challenges of increasing offshore wind turbine size. You can register for future webinars through our events page at wind.ny.gov. We also encourage you to check out past webinars in the series on NYSERDA's website and YouTube channel. If you have requests for future topics you would like to hear about in the series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on our website. Thank you for joining us today, and we'll see you next time.